Good day. Today we begin our math course, and this first lesson concerns itself with approximate numbers and the rules for significant digits. So first of all, I've got a document that I've prepared. There's a copy of this document posted for you in Blackboard. And we're going to start just at the top of the page where we make a distinction between what an approximate number is as opposed to an exact number. So approximate numbers are those determined by measurement. So for example, if you take a protractor and you use it to measure an angle, the number of degrees determined would be an approximate number. And you'll encounter approximate numbers in the laboratory also. So if you're using an ammeter to measure current, the number of amps resulting would also be considered approximate. We can contrast that with exact numbers. These are determined by counting or also by definition. So what I mean here is in a traditional semester, I could actually physically count the students present on any given day, and that number of students would be an exact number. When we talk about those numbers determined by definition, this is like saying there are 7 days in a week. That would be exactly 7. Similarly, 24 hours in a day, that's defined to be exact. So the rest of this lesson concerns itself with those numbers that are approximate. And when we have approximate numbers, we often are concerned with how many significant digits are there in that approximate number. So there are 4 rules listed here. What I'm going to do is read the rules with you first, and then we're going to go and do some practical examples to highlight the rules. So rule 1, all non-zero digits are significant. So this would be any number from 1 through 9. Rule 2, zeros located between 2 significant digits are significant. Rule 3, leading zeros are not significant. So we need to be aware of what a leading zero is. These are the zeros that come first at the front of the number before any non-zero digits. And they are not significant. Rule 4 is the most difficult case because trailing zeros are sometimes significant and sometimes they are not significant. So trailing zeros will come at the end of the number. So all the zeros located at the end of the number. So these zeros are significant when they are to the right of the decimal. But when they are not to the right of the decimal, they are not significant. Okay, so let's pause there. We'll refer back to this handout again later, but let's pause there to look at some examples. Okay, so we're going to start right up here at the top of the page and just go through this exercise together. Determine the number of significant digits in each. So looking at this first number, 35.46, we should say that all 4 digits there are significant. In fact, they are all non-zero, so they are all significant. This number, 600.08, has 5 significant digits. The zeros, the 3 zeros, are located between the 6 and the 8, and therefore they count as significant. That's rule 2 on our list. Okay, let's look at this number, 0.007. Now, all 3 of these numbers are leading zeros because they all come first before this first non-zero digit. So they are all called leading zeros, and therefore none of them are significant. That's rule 3. Leading zeros are not significant. So we have only one significant digit there. Okay, this number, 7,500. These two zeros are called trailing zeros because they come at the end of the number. Now, once we determine that they are trailing, we have to determine if they are to the right of the decimal. In this case, they certainly are not to the right of the decimal. The decimal would be here at the end of the number. So these are trailing zeros that are not to the right of the decimal, and therefore they are not significant. So this is rule 4 that has only 2 significant digits. Now the next example is 7,500 once again, but over the last zero is a bar, a little bar drawn. This little bar is actually called a vinculum. And what it does is it changes the number of significant digits illustrated. So with the bar here over the last zero, we would now say that there are 4 significant digits in 7,500. Okay, and if, for example, 7,500 were written this way, with the vinculum over this zero, now we would have 1, 2, 3 significant digits in total. Okay, so using the vinculum can change the number of significant digits. So with no vinculum, 2 significant digits. With the vinculum here, 3 significant digits. With the vinculum here, 4 significant digits. Okay, let's look at this last one, 40.0. Now, we have to determine what kind of zeros these are. These are trailing zeros. Now, remember the rule for trailing zeros. They are significant if they are to the right of the decimal. So this one is to the right of the decimal, so it is significant. The 4 is certainly also significant because it is non-zero. But you cannot have this number significant, this one significant, and the one in between non-significant. That never happens. So by virtue of this one trailing zero being to the right of the decimal and significant, we now have all 3 numbers here significant. So there are 3 significant digits in 40.0. Okay, the next thing we're going to do is a little rounding exercise. So for these examples here, we are going to round each to 3 significant digits. Okay? And we're going to express our answer 2 ways. First in ordinary notation and then in scientific notation. All right, the first thing we have to do is actually locate the 3rd significant digit. So let's start with this one. These are non-significant because they are both leading zeros. As soon as they're called leading zeros, they are non-significant, and it doesn't matter if they are located to the left or to the right of the decimal. If they are leading, they are non-significant. And certainly, you can read that again in Rule 3. Leading zeros are not significant. Okay, so that means we start counting here. 1, 2, 3. So the 2 is the 3rd significant digit. In order to round, you simply look 1 digit to the right. If it is 5 or more, this number rounds up. Okay, so yes, this is certainly 5 or more. So this number here rounds up to a 3. So we end up with 0.0483. So that's the number rounded. Okay, you can see there are 1, 2, 3 significant digits now. To express it in scientific notation, we have to locate the decimal after the first non-zero digit. So the decimal will have to be right here after the 4. So that will look like this, 4.83. Now, of course, we have to include the appropriate power of 10. So 4.83 times 10 to the decimal moved 2 places. You can see that right here, 2 places. So this has now an exponent of -2. The exponent is negative when the number is less than 1. Okay? So if we were going to convert this to an ordinary number, this would tell me to move the decimal 2 to the left, in which case it would match. Okay, let's try this other one, 8,463. So first we circle the third significant digit, 1, 2, 3, right there. We look to the right of that number. This number is not 5 or more, which means this 6 does not round up. It remains a 6. So 846. However, this number was more than 8,000. This number is only 800, a little more than 800. We cannot forget the placeholder 0 here. Okay, so the number rounded to 3 significant digits is 8,460. The 0 here is trailing. It is not to the right of the decimal. The decimal would be here. So it is non-significant. So this is perfect. We have 3 significant digits. In scientific notation, we have to locate the decimal after the first non-zero digit. That means the decimal has to go here. So 8.46. We have to include the correct exponent. And from here to here is 3 places. Okay, the exponent is +3. This number is greater than 1. The exponent is +3. Okay, next one. Find the third significant digit, 1, 2, 3, right here. The 8 tells us to round the 9 up. When it rounds up, it will be a 10. So we get 6.10. Is this 0 required? It is, because we need to show 3 significant digits, 1, 2, 3. This 0 is significant because it is a trailing 0, since it's at the end of the number, and it is also to the right of the decimal. What is this number written in scientific notation? Well, the decimal is already correctly located after the first non-zero digit. So if we had to include a power of 10, the exponent would have to be 0. Okay, 10 to the 0, of course, is equal to the whole number 1. The 0 telling you we do not move the exponent left or right. Okay, let's try this one. 1, 2, 3, circle it, underline, okay. The 6 telling us that the 9 will round up to a 10, but then of course that will round this 9 up as well. So we will end up with 400,000 here as our result. However, 400,000 written like this shows only 1 significant digit. These are all trailing zeros, but they are all to the left of the decimal. The decimal would be here, and therefore they are non-significant. So this number right now shows only 1 significant digit. So how do we bump it up to 3? We include a vinculum. The vinculum would go right here. so that we would have 1, 2, 3 significant digits. So the little bar goes over that second 0. In scientific notation, we locate the decimal right after the 4. We would include 2 zeros, which are required to show 3 significant digits. What would be the corresponding power? It would be 10 to the 5. It is 5 decimal positions from here to here. 1, 2, 3, 4, 5. So 4.00 times 10 to the 5. Okay, I'd like to suggest at this point that you pause the video and try these 4 now on your own. Okay, so go ahead and do that. Pause the video, try the next 4, filling in both columns. And then when you're done, you can unpause the video and check, because I'm about to fill in the answers now for these next 4 examples. Okay, so pause it, try them, and then refer back to see if you've got the correct results. Okay, so you can see that for each example, I began by circling the 3rd significant digit. Then I rounded up for this one, and this one. This one did not round up because the number 4 is not 5 or greater. Okay, so then these numbers are now appropriately rounded, and they also show 3 significant digits each. Then I put each in scientific notation. So locating the decimal after the first non-zero digit, and finally including the correct exponent. So in this case, positive 4, here negative 1, here positive 1, and here negative 2. So check your own very carefully against these to make sure that you've grasped that concept. Okay, the next thing that we have to do is take a look at the difference between accuracy versus precision for an approximate number. So we'll go back to our handout. It says, the accuracy of an approximate number is given by the total number of significant digits present, whereas the precision is given by the position of the rightmost significant digit. Okay, and a quick note at the bottom here that we're talking about approximate numbers in our next examples that follow. If it were an exact number, it would be said to have infinite precision and infinite accuracy. Okay, but anyway, let's have a look at the difference between these two important measures. So what we're going to do in each of these examples is state which number is more accurate, then state which number is more precise. Okay, so in our first example, the numbers that we are comparing are 0.041 and 7.62. So in part A, first, we're going to compare the numbers for accuracy. So we simply have to record how many significant digits are present in each. In this number, there are only 2 significant digits. These zeros are leading. Leading zeros are never significant. This number, on the other hand, has 3 significant digits. They are all non-zero and therefore all significant. So what does this mean? It simply means that the number 7.62, okay, so this is therefore 7.62 is more accurate. Okay, simply because it has 1 more significant digit. Okay, but now we're going to compare the numbers for precision. So we start by circling the rightmost significant digit. The rightmost significant digit. And then we talk about its position in the number. So hopefully you remember a little bit about place value. So a number here is in the tenths column. This is hundredths. This is thousandths. So we say that this first number is precise to the nearest thousandth. Okay, tenths, hundredths. While the second number, 7.62, is precise to the nearest hundredth. Okay, so what does this mean? It means that the first number is more precise. Okay, so we had 2 numbers. One of the numbers was more accurate, the other is more precise. Okay, so you can think of it as 3 decimal places versus 2 decimal places. Okay, but we say precise to the thousandth versus precise to the hundredth. Okay, here's another example. The numbers we're comparing are 50.060 and 8.914. Okay, so first of all, we have to determine how many significant digits are in each because we are comparing them for accuracy. So how many significant digits are here? The 5 is significant, the 6 is significant. So certainly the zeros in between them are also significant. Okay, so for sure 4 significant digits. The question is, do we count this 0? It is called trailing because it's at the end of the number. It is also to the right of the decimal. The decimal is here, so it is certainly to the right of the decimal. Trailing zeros to the right of the decimal are significant. So we have 5 significant digits here versus 4 significant digits here. So what's the conclusion? That first number is more accurate. Okay, now we'll compare the 2 numbers for precision. We circle the rightmost significant digit in each. And now we compare their location. That is the thousandths column. That too is the thousandths column. So both numbers are precise to the nearest thousandth. And so what is the conclusion? The numbers are equally precise. So one number is more accurate, but they are equal in their precision. Okay, a final example. The first number is 725,000. We're comparing that with 10.5. Let's compare them first for accuracy. How many significant digits are here? Only 3. These 3 trailing zeros are not to the right of the decimal. The decimal would be here, so the 3 trailing zeros are left of the decimal and are therefore not significant. Here we also have 3 significant digits. 2 are non-zero and 1 zero between. So all 3 significant. So what does that mean? It means the numbers are equally accurate. Are they also equally precise? To figure that out, we have to start by circling the rightmost significant digit. Which is the rightmost significant digit? This one. What column is that located in? Well, remember, the decimal would be here. This is the ones column, tens column, hundreds column. This is the thousands column. So that number is only precise to the nearest thousand. Here is the rightmost significant digit in 10.5. Which column is that 5 located in? It is located in the tenths column. So this number is precise to the nearest tenth. So in fact, it is quite a bit more precise than the other number. So we can say 10.5 is more precise. In fact, you could say it's way more precise if you like. Okay, way more precise because we're comparing the tenths column with the thousands column, which is much further along to the left. Okay, so I hope those concepts were clear for you today. You can try the suggested problems from your textbook. They're from exercises 1.3. I'm going to have a posting in Blackboard just along with this video with the questions that I would suggest you try. I'm also going to be posting the solutions that accompany your textbook. Okay, so you'll be able to try the recommended problems and you'll also be able to check your solutions. Okay, thanks a lot for watching today and please give those questions a try.